shows that the age does not have a significant influence on the network. When you look at diagram 2, it looks like the mileage is solely responsible for creating the regression plane. Dave suspects the problem is that the input values age and mileages have orders of magnitude differences. He decides to normalize the data. What is normalizing data? Let me show you an example. On the left you see the age in years. The values go from 0.2 to 5.2. Normalizing these values would put them between 0 and 1. Dave uses his spreadsheet skills to achieve this. Here is the result. Dave does the same for the mileage. Two columns are added to the spreadsheet, the normalized ages and the normalized mileages. The normalized values will now be used as training data. If you are curious, here are the formulas Dave used to normalize the age and mileage columns. If you decide to use a library like NumPy, you can use NumPy's normalize function to do this for you. Let's put the normalized values in the code. I start by removing these predictions. I paste the normalized training inputs. Let's execute the code. Nothing much has changed. But that is probably because the learning rate is so low. I'll set the learning rate to 0.1. This should bring the weights and bias up. The weights and bias went up. But what does that mean? We normalize the inputs and the relationship between input and output is now difficult to see. So let's take the weights and bias and use them to plot a regression plane again. This time you see that both the age as well as the mileage influence the maintenance costs. It's time to test the system to see how well we are doing. Dave creates 5 test cars with the expected maintenance costs. Notice the car with a high age and low mileage, and the car with a low age and high mileage. Dave is curious if the network can predict the maintenance costs for these anomalies. He normalizes the values according to the normalization formula he used before. And now it's time to test the system. I don't want to print the weights and bias anymore, so I'll remove this line. I'll paste the test data and use the data to make test predictions. Let's see how well the network can predict with the normalized values. That is very good. The predicted values are really close to the target values. Even anomalies like old cars with low mileages are predicted well, as well as young cars with high mileages. Normalizing helped us to create good results, but one thing I'd like to repeat is that a neural network is not done when the inputs are sanitized. As you have seen, I have adjusted the learning rate and epochs many times to find the right values. This is why it is so important to learn how neural networks work from the ground up. Even if you later decide to use a machine learning library, knowing the purpose of the parameters of the network is going to benefit you. At this particular point in the story, I'd like to remind that what we did is to create a neural network that looks intelligent. Artificial intelligence is not really intelligent. As you have learned, it is a collection of functions, parameters, and training data that mimics intelligence. Dave does not have to worry that his car prediction software will take over the world anytime soon. As for us, we have some refactoring to do. We are going to make the network more generic, and I will explain a hot topic in neural networks: gradient descent.